the speed of light. It feels like the one thing in the universe that's set in stone. A rule that can't be broken. We call it K. It's the ultimate speed limit. Nothing with mass can reach it. And nothing at all can go faster. But is that really true? Is it a permanent, unchangeable law of nature? Or is it something more flexible? Could the speed of light be changed? The short answer is yes, and also no. That sounds like a cop-out, but it's the honest truth. It all depends on what you mean by the speed of light. Let's start with the easy part. The eyes. Light absolutely slows down. It happens all the time. The famous speed, 299,792,458 meters per second, is the speed of light in a perfect vacuum, when there's nothing in the way. But the universe isn't a perfect vacuum, it's full of stuff. And when light travels through stuff, it slows down. When light hits a glass of water, it slows down by about 25%. When it travels through a diamond, it slows down by more than half. This is a real, measurable change in speed. It's the reason lenses can focus light and prisms can split it into a rainbow. The phenomenon is called refraction. It's a basic property of optics. But something strange is happening here. The light itself, the individual particles of light called photons, are not actually slowing down. A photon can only ever travel at one speed. That speed is... it can't go at C minus a little bit. It's all or nothing, so how can the beam of light slow down if the photons that make it up don't? It's about interaction. Think of it like a celebrity walking through a crowd. The celebrity can only walk at one speed. But they keep getting stopped by fans to take a photo or sign an autograph. They walk a few steps at their normal speed, then stop, interact, and then walk a few more steps at their normal speed. From a distance, if you just watch their overall progress across the room, it looks like they are moving very slowly. But their actual walking speed between stops never changed. That's kind of what happens to light in a material like glass or water. A photon zips along ETSA until it hits an atom. The atom absorbs the photon's energy. For a tiny fraction of a second, the photon ceases to exist. The atom holds onto that energy, gets excited, and then after a brief pause, it spits out a brand new photon with the exact same energy and direction as the old one. This new photon then zips along at c until it hits another atom. The process of absorption and re-emission creates a tiny time delay at every atom the light encounters. There are trillions of atoms. These tiny delays add up. The net effect is that the overall signal, the wave of light, travels through the material at a slower speed. The photons themselves are always moving in the empty space between atoms. But the overall journey is delayed. So yes, we can change the speed of light. We do it every time we put on a pair of glasses. Scientists have taken this to an extreme. In a lab, they can create a special state of matter called a Bose-Einstein condensate. It's a cloud of atoms chilled to a temperature just a sliver above absolute zero. At this temperature, the atoms almost stop moving and start to act in a weird collective way. In the late 1990s, a team led by physicist Lene Howe managed to pass a laser beam through one of these clouds and slow the light down to about 17 meters per second. That's about the speed of a car in a school zone. Later, they got it to stop completely. They could hold the light pulse in the cloud for a moment and then release it. It's an amazing achievement. But it's important to remember what they were doing. They were not changing the universal constant. They were just making the crowd of atoms incredibly sticky. They were maximizing the interaction delay. The fundamental speed limit of the universe remained untouched. So that brings us to the hard part. The no. Could we change the actual value of c, the speed of light in a vacuum? Not just slowing it down in a medium, but changing the number itself. Could we turn a dial and make faster or slower everywhere in empty space? According to all of our current, tested, and proven physics, the answer is a firm no. The speed of light isn't just some random number. It's not just the speed of photon. It's woven into the very fabric of space-time. It's the speed of causality itself. Before Einstein, people thought of light as just another wave. James Clerk Maxwell, a Scottish physicist in the 1860s, was the first to figure out what light really was. He unified the equations of electricity and magnetism, and he found something amazing buried in the math. He found a wave, an electromagnetic wave. His equations predicted its speed based on two other constants of nature. One that described the strength of the electric force in a vacuum, and one that described the strength of the magnetic force in a vacuum. When he calculated the speed of this wave, the number that popped out was the known speed of light. This was a huge revelation. Light was a ripple in the electromagnetic field, and its speed wasn't arbitrary. It was a direct consequence of the fundamental properties of empty space. To change the speed of light in a vacuum, you would have to change the electrical or magnetic properties of the vacuum itself. You'd have to change the nature of reality. Then came Albert Einstein. He took this idea and ran with it. He built his entire theory of special relativity on two core ideas. One, that the laws of physics are the same for everyone who is not accelerating. And two, that the speed of light in a vacuum is the same for everyone, no matter how fast they are moving. That second idea is the weird one. It goes against all our intuition. If you're on a train moving at 100 miles per hour and you throw a baseball forward at 50 miles per hour, someone standing on the ground sees the baseball moving at 150 miles per hour. Speeds add up. But Einstein said this doesn't work for light. If you're on a spaceship moving at half the speed of light and you turn on a flashlight, you don't see the light beam shoot away at 1.5 times the speed of light. You see it move away at exactly c, and someone watching you from a stationary planet also sees that same beam of light moving at exactly. It seems impossible. How can something have the same speed relative to two different observers who are moving relative to each other? The only way the math works is if something else gives. That something else is space and time. To keep, say, constant for everyone, space and time themselves must become flexible. For the person on the fast-moving spaceship, time slows down and distances in the direction of motion shrink from the perspective of the stationary observer. It's not an illusion, it's a real physical effect. GPS satellites have to account for this. Their clocks literally tick at a different rate than clocks on Earth, and if we didn't correct for it, GPS would be off by miles every single day. And from this constancy offs comes the most famous equation in all of science. EMC2. Energy equals mass times the speed of light squared. This equation tells us that mass and energy are two sides of the same coin. And the conversion factor between them is squared, a very, very big number. This is why a small amount of mass can release a tremendous amount of energy in a nuclear bomb or a star. So, it is not just a speed, it's a fundamental conversion factor for the universe. It tells us how much space is equivalent to how much time. It tells us how much energy is equivalent to how much mass. It is the bedrock of relativity, which is our best description of gravity and the universe at large scales. Changing wouldn't be like changing the speed limit on a highway. It would be like changing the definition of a mile or an hour while you're driving. The entire system would collapse. What would actually happen if we could magically change? Let's imagine we had a dial. If we turn the dial down, making smaller, MXT2 tells us that the amount of energy released from any mass would decrease dramatically. The nuclear fusion that powers the sun is a delicate balance. Hydrogen atoms fuse into helium, converting a tiny bit of their mass into a huge amount of energy. If K were lower, they would produce less energy. The sun would cool down and dim. It might even extinguish. All stars would. The universe would go dark and cold. It gets worse. The structure of atoms themselves depends on K. There's another fundamental number called the fine structure constant. It's a dimensionless constant, a pure number, about 1/137. It describes the strength of the electromagnetic force that holds atoms together. This number is derived from a combination of other constants, including the charge of an electron, Planck's constant, and the speed of light. If you change T, you change the fine structure constant. If you change that, you change the rules of chemistry. Electrons might orbit the nucleus at different distances. The bonds between atoms that form molecules might become weaker or stronger. Complex molecules like DNA might fall apart, or maybe they could never have formed in the first place. The very existence of matter as we know it, the stability of the elements, is tied to the value of K. A difference means a different universe, and almost certainly one without life. If we turn the dial up, making higher, the consequences would be just as catastrophic. EMNC2 means that stars would suddenly become much, much more energetic, the sun would burn hotter and brighter, likely incinerating the Earth. Massive stars would burn through their fuel in an instant and explode. So, according to our best understanding, is fixed. Or changing it would break the universe. But what if our understanding is incomplete? This is where science gets interesting. There are some physicists who have seriously proposed that the speed of light might not have been constant throughout all of cosmic history. These are called varying speed of light, or VSL theories. They are not mainstream ideas. Most physicists don't think they are correct, but they are a serious attempt to solve some big puzzles in cosmology. One of those puzzles is called the horizon problem. When we look out at the universe, we see the cosmic microwave background. It's the leftover heat from the Big Bang. And the astonishing thing is, it's almost perfectly the same temperature in every direction we look. It's uniform to 1 part in 100,000. This is very strange. If we look at one side of the observable universe and then the other, those two regions are almost 28 billion light years apart from each other. The universe is only about 13.8 billion years old. There hasn't been enough time for light, or any information, to travel from one side to the other. So, how did they know to be the same temperature? How did they reach thermal equilibrium if they were never in contact? The standard solution to this problem is a theory called inflation. It says that in the very first fraction of a second after the Big Bang, the universe underwent a period of hyperfast expansion, growing exponentially in an instant. Before this inflation happened, the entire observable universe was a tiny subatomic patch where everything was in contact and could even out its temperature. Then inflation blew it up to enormous size, preserving that uniformity. Inflation works well mathematically, but we don't really know what caused it. VSL theories offer a different solution. What if, in the very early universe, the speed of light was much, much faster? Maybe trillions of times faster than it is today. If he was huge, then light could have easily crossed the entire baby universe in the time available. The distant regions could have communicated and evened out their temperature. Then, as the universe expanded and cooled, the speed of light slowed down and settled into the value we see today. This is a radical idea. As we saw, changing messes with everything, including general relativity. Proponents of VSL, like the physicist João Magejo, have had to try and build a whole new version of relativity where it can change without breaking everything. It's incredibly difficult. It raises more questions than it answers. For example, how and why did slow down? What mechanism controlled it? For now, VSL remains a fringe, speculative idea, a clever what if. There's no evidence for it. And there's a lot of evidence against it. How do we know kid hasn't changed? We can look back in time. The universe is a time machine. When we look at a galaxy that is 1 billion light years away, we are seeing it as it was 1 billion years ago. The light from that galaxy carries a fossil record of the laws of physics at that time and place. Astronomers can do this by looking at the fine structure constant. They can look at the light from incredibly distant quasars, which are bright galactic cores. As that light travels towards us, it passes through gas clouds and galaxies billions of light years away. The atoms in those clouds absorb very specific frequencies of light, leaving a pattern of dark lines in the spectrum, like a barcode. The exact spacing of these lines depends on the value of the fine structure constant in that ancient gas cloud. If the speed of light was different back then, the fine structure constant would have been different, and the spacing of the lines in the barcode would be different from what we measure in labs on Earth today. For decades, these measurements have shown no change. The fine structure constant appears to be the same everywhere, and at every time we've been able to measure it. In the early 2000s, one team of astronomers, led by John Webb, claimed to have found a tiny variation. They suggested that the constant might have been slightly smaller billions of years ago. It was a tantalizing result that caused a lot of excitement, but other teams using different telescopes and different methods have not been able to replicate it. The vast majority of the evidence still points to being an absolute unchanging constant. There's also evidence from a natural nuclear reactor. About 2 billion years ago in what is now Gabon, Africa, a rich deposit of uranium ore happened to have the right concentration and conditions to start a spontaneous, slow, self-sustaining nuclear fission reaction. It ran for hundreds of thousands of years. We can analyze the waste products of this natural reactor today. The ratios of different isotopes left behind are extremely sensitive to the laws of nuclear physics, which in turn are sensitive to the fine structure constant. The analysis shows that the constant, and therefore, was the same 2 billion years ago as it is today, to an incredible degree of precision. So, let's circle back to the original question. Could the speed of light be changed? If you mean slowing a beam of light down by passing it through a material, then yes. We can slow it to a crawl, and even stop it in a laboratory. But we are not changing the universal speed limit. We are just creating a cosmic traffic jam. If you mean changing the fundamental value of steam in a vacuum, the speed limit of the universe itself, the answer is no. All of our confirmed physics says it is an absolute constant. It's not a speed limit in the way a sign on the road is a speed limit, something that is imposed on reality. It seems to be a fundamental feature of reality. It's the speed of cause and effect. It's the exchange rate between mass and energy, between space and time. To change it would be to rewrite the source code of the cosmos. Our universe is built upon the laws of relativity and quantum mechanics, and the constants is the bridge that connects them. It shows up in every corner of physics. Its value seems to be precisely what's needed for a stable universe with stars, planets, and chemistry. Could it have been different in the past? It's a remote possibility. A few scientists are exploring the idea. But the evidence we have from looking at distant galaxies and ancient nuclear reactions tells us it has been the same for a very long time. It's one of those beautiful things about the universe. There's so much chaos and complexity. Stars are born and die, galaxies collide. But some things are simple, constant, and reliable. The speed of light is one of them. It's a fixed point in a changing reality. It's the ruler by which we measure everything else. And while it would be exciting to think we could change it, the fact that we can't is probably the only reason we're here to ask the question in the first place. The universe, as we know, it depends on staying right where it is.